Hello, and welcome to the sleepy universe. Imagine a shoreline late at night when the tide has slowly drawn away, leaving behind a thin layer of water that reflects the sky. Waves slide gently onto the shore, pause for a moment, and dissolve before another begins the same familiar journey. Above, stars are scattered across the darkness. Below, countless grains of cool, fine sand rest beside one another, stretching toward the place where the fading light can no longer clearly distinguish sea from land. If you were to bend down and lift a handful of sand, what rested in your palm might not seem especially remarkable. They would simply be tiny grains of gray, brown, or nearly transparent material, shaped by seawater, wind, and time through countless collisions. They do not glow. They do not move in any way the human eye can recognize. And within the vastness of the universe, a grain of sand may seem like one of the most ordinary things we could imagine. Yet inside that tiny object are atoms the universe was once unable to create. Many grains of sand contain minerals formed from silicon and oxygen, along with smaller amounts of iron, magnesium, calcium, carbon, and many other elements. Today, these elements are present almost everywhere around us. They are found in the rocks beneath our feet, in the soil that nourishes plants, in the buildings of our cities, in the water of the oceans, and within living bodies themselves. Their presence is so familiar that it is easy to imagine they have always been here, as though the universe were born with all the ingredients needed to make dust, stone, and planets. But the early universe was nothing like that. There was once a time with no shorelines, no mountains, no soil, no crystals of ice drifting through space, and no grains of sand for any hand to pick up. It was not only that solid worlds had not yet formed, most of the atoms required to build them had not yet appeared. The universe was younger then, hotter, and far simpler than the one we inhabit today. The ordinary matter of that earliest era consisted mainly of hydrogen and helium, along with a very small amount of lithium and a few other light isotopes. It was a universe filled with gas, radiation, gravity, and regions of matter that were gradually becoming denser, but it contained almost none of the ingredients needed to create complex solid material. There was not enough silicon to form silicate minerals, not enough carbon to create carbon-based dust grains, and no iron to become part of rocky planets or sink into planetary cores that still belong to a very distant future. Dust in that age had not been swept out of space by some unseen force, nor was it hidden in the darkness, waiting for the first telescopes sensitive enough to find it. Dust simply could not yet exist, because the universe had not created the necessary ingredients, nor had it passed through the conditions that would allow those ingredients to combine into solid matter. This makes a grain of sand resting in your palm the final part of a story older than any ocean, continent, or planet. Before that grain could exist, the universe first had to form its earliest stars. Inside those stars, light elements had to be heated and transformed into carbon, oxygen, silicon, and many heavier elements. Then, the newly created material had to escape from the place where it was born, enter interstellar space, expand, cool, and begin bonding in ways that had never been possible before. And even after those ingredients appeared, a dust grain did not form immediately. A silicon atom drifting through a stream of hot gas was not yet a mineral grain, just as a carbon atom, newly released from a star, was not yet a solid object. Those atoms had to meet under the right conditions. They had to lose enough energy for their bonds to survive instead of breaking apart as soon as they formed. Gradually, they had to build clusters stable enough for more atoms to attach themselves. Only from beginnings too small to be observed individually could the first solid particles begin to emerge. Even after forming, they still faced another challenge: surviving long enough to enter interstellar space. Some grains may have condensed within cooling layers of gas surrounding an aging star, while others may have appeared in matter expelled as a star reached the end of its life. Yet the very environments that created them also contained intense heat, powerful radiation, and shock waves capable of eroding newborn grains, shattering them, or returning them to a gaseous state. The history of dust, then, is not only the story of how solid matter formed, it is also the story of how the first fragile structures survived within a universe that was still violent and unstable. Today, we cannot travel back to directly observe the exact moment when the first dust grain came into being. Light from that era has crossed space for more than 13 billion years. While those earliest particles may have been destroyed, remade, mixed together, or drawn into new generations of stars long before the solar system appeared. Yet their story has not vanished completely, because matter leaves traces in light and in the chemical composition of every place through which it has passed. Astronomers search for those traces in the infrared light of distant galaxies, in the spectra of aging stars, and in the clouds of material left behind after stellar explosions. They study how dust absorbs light, how it releases that energy again at wavelengths invisible to the human eye, and how elements are distributed through environments poor in heavy elements. Observations from the James Webb Space Telescope are also revealing that the universe may be able to create dust through more flexible pathways than we once imagined. Even within galaxies whose chemical composition remains relatively primitive and contains only a small fraction of the heavy elements found in the Milky Way. These discoveries gradually lead us back to a larger question. How did a universe made almost entirely of hydrogen and helium become a place filled with rocks, planets, oceans, and eventually living beings capable of standing on a shoreline, holding a grain of sand in one hand, and wondering where its journey began? To search for the answer, we will leave this imagined shore behind and follow the history of matter backward through time. We will pass through the disks of gas and dust where planets are assembled, through cold clouds between the stars, through material returned to space by aging suns, and deep into the nuclear furnaces of the earliest stellar generations. In the end, this journey will carry us back to an age so distant that the entire universe contained no solid surface at all. Even though light had already begun to travel through space, and gravity was quietly gathering gas into the first structures. It was a universe with matter, but no stone, with light, but no sand, and with vast oceans of gas in motion, while not a single grain of dust had ever drifted through the darkness. From that almost absolute simplicity, the story of every solid world began. If it were possible to stand outside time and look back at the universe during its earliest stages, what might seem most surprising would not be the absence of human beings, Earth, or the familiar galaxies, but the absence of almost anything with a surface. There was not a single rock drifting through the darkness, not a grain of sand worn smooth by water, not a layer of soil capable of holding a footprint, and not a fragment of metal reflecting light. The universe was not completely empty, but everything within it existed in a far simpler state, mainly as radiation, gas, and regions of matter slowly responding to the pull of gravity. To understand why dust could not yet exist, we need to return to a very early moment, just after the universe had passed through the first few minutes of its expansion. In that hot, dense environment, fundamental particles collided continuously, and temperatures were too high for most complex structures to remain stable. As the universe gradually cooled, protons and neutrons began combining to form the nuclei of light atoms. This process, commonly known as Big Bang nucleosynthesis, lasted for only a relatively brief period, but it established the first chemical composition of the entire universe. Most ordinary matter became hydrogen, the simplest element, with a single proton in its nucleus. A smaller portion became helium, usually containing 2 protons and 2 neutrons. There were also tiny amounts of deuterium, helium-3, lithium, and a few other light isotopes, but compared with hydrogen and helium, they were little more than faint specks against an almost uniform background. By mass, roughly 3/4 of the early universe's ordinary matter was hydrogen and nearly 1/4 was helium, while everything else made up only a very small fraction. Those proportions may sound sufficient to create a rich and varied universe, because hydrogen is now found in water. Helium exists within stars, and both play important roles in nature. Yet hydrogen and helium alone are not enough to form a solid grain of dust, a stone, or a planet like Earth. Hydrogen is extremely light, and under most conditions in space, it exists as individual atoms or as molecules of gas. Helium is even less reactive, because its stable electron structure means that it rarely forms chemical bonds with other elements. A universe containing only these two ingredients could form clouds of gas, stars, and eventually larger structures, but it did not yet possess the chemical diversity needed to build complex solid objects. The grains of sand along a shoreline often contain large amounts of silicon and oxygen, joined together in stable crystal structures. Rocky planets require magnesium, iron, aluminum, calcium, and many other elements to form their crusts, mantles, and cores. Carbon dust requires carbon, while many silicate grains require silicon, oxygen, magnesium, and iron. None of these elements existed in significant amounts immediately after the Big Bang. The universe had matter, but not enough kinds of matter. It had atoms, but the periodic table was still almost empty. Astronomers often use the word metal in a much broader sense than we do in everyday life. In astronomy, nearly every element heavier than helium may be described as a metal, including carbon and oxygen, even though ordinary chemistry does not classify them that way. By this definition, the earliest universe contained almost no metals at all. Its metallicity was close to zero, because no generations of stars had yet lived long enough to create heavy elements and release them into space. This also meant that one of the most familiar sights in the modern universe, the dark clouds of dust that obscure the light of stars behind them, could not yet exist. Today, when we look toward the Milky Way, we often see long dark bands stretching between countless stars. Those dark regions are not empty. They are clouds of gas and dust where light is absorbed or scattered before it can reach our eyes. In the primordial universe, gas was already present, but dust was almost entirely absent. Light moved through matter in a different way, and clouds could cool through a much more limited set of processes. After the first few minutes, the universe continued expanding for hundreds of thousands of years. Its temperature steadily fell, but it remained hot enough for electrons to move freely and repeatedly collide with light. Space was not transparent like the night sky we imagine today, because photons were constantly scattered by electrically charged particles. Only when the universe cooled to a few thousand degrees could electrons bind stably to hydrogen and helium nuclei, forming neutral atoms. This event is commonly called recombination, even though historically, those particles had never before remained stably combined. Once electrons no longer obstructed light in the same way, radiation could travel more freely through space. That ancient light can still be observed today as the cosmic microwave background, stretched into microwave wavelengths by more than 13 billion years of cosmic expansion. It is like a very early photograph of the universe, showing no fully formed stars or galaxies, but instead an almost uniform field of matter marked by extremely small differences in density. Those tiny differences carried enormous importance. Some regions contained slightly more matter than their surroundings, and gravity began to amplify the imbalance. A slightly denser region attracted more material, became denser still, and continued drawing in additional gas. This process unfolded very slowly on human timescales, but across tens and hundreds of millions of years, it gradually transformed a relatively uniform universe into a vast network of filaments, empty regions, and gathering places that would eventually become galaxies. Most of the mass involved in this process did not shine and did not form the familiar atoms around us. It was dark matter, a form of matter whose true nature remains unknown, but whose presence can be recognized through its gravitational effects. Dark matter created gravitational regions, like invisible frameworks within which hydrogen and helium gas gradually collected. It did not form dust or stone, and it did not participate in chemistry the way ordinary matter does. Yet without its gravity, the first structures might have followed a very different history. For hundreds of millions of years, after the background radiation separated from matter, the universe entered a period commonly known as the Cosmic Dark Ages. The name does not mean that light was entirely absent, because ancient radiation still filled space. But no stars had yet begun shining through nuclear reactions in their cores. There were no bright points like the stars in today's sky, no luminous galaxies, and no clouds of dust reflecting the blue light of young stars. There was only primordial gas drifting, cooling, and slowly falling into gravitational wells that were growing ever deeper. If we could shrink the early universe into an imaginary ocean, it would not be an ocean with a surface, a seafloor, or sandy shores. It would be a boundless ocean of gas, where the waves were created not by wind, but by tiny differences in the density of matter. Denser regions would resemble enormous, slowly turning currents that drew in the surrounding gas, while other areas became increasingly empty. Every movement unfolded in silence, because sound could not travel across the vast spaces between the clouds of gas, and there was no observer there to hear it. The absence of dust made the contraction of the first gas clouds very different from the process of star formation in the Milky Way today. In modern clouds, many atoms, molecules, and dust grains can absorb energy and release it again as radiation, allowing the gas to cool. As the gas loses heat, its pressure falls, and gravity can compress the material more efficiently. Dust also shields the inner regions from intense radiation, allowing fragile molecules to survive for longer periods. But in the earliest universe, most of those mechanisms did not yet exist. The gas had only a few ways to lose. Atomic hydrogen could emit radiation under certain conditions, and small amounts of molecular hydrogen could form, helping the gas cool further. Even so, cooling remained far less efficient than it is within the dust-rich, metal-rich clouds of the present era. As a result, primordial regions of gas may have needed to gather much larger amounts of matter before they could begin fragmenting and collapsing with great intensity. This is one reason scientists believe that many of the first stars may have been extremely massive. Even so, the idea must be expressed with care. We have never directly confirmed an individual population 3 star, and current models do not necessarily predict that every first-generation star was enormous. Some may have been smaller than early estimates suggested, and their distribution of masses remains an open question. What can be said with greater confidence is that they formed in an environment almost entirely without heavy elements or dust, one profoundly different from the region where the sun would be born billions of years later. When we imagine a universe without dust, it is also easy to fall into another misunderstanding, that the absence of dust meant the absence of structure. In reality, the universe began building structure very early. Dark matter formed regions of gravitational attraction. Gas fell into those regions, large clouds gathered, and a cosmic web slowly emerged. What was missing was not motion or organization, but chemical richness. The universe already possessed a primitive architecture, but it did not yet have the materials needed to complete the finer details. It was like an infinitely large construction site, supplied with only 2 kinds of material. With hydrogen and helium, nature could build immense clouds of gas and ignite them into stars, but it could not yet create rocky crusts, crystals, liquid oceans, or complex organic molecules. Those possibilities were not forbidden by the laws of physics, but they had to wait until another generation of structures appeared and began changing the composition of the universe. How can we know that such a distant era consisted mainly of hydrogen and helium, when no one can collect a sample of gas from the early universe and carry it into a laboratory? The answer lies in the fact that many independent clues point toward the same picture. Models of Big Bang nucleosynthesis predict the proportions of light elements based on the temperature, density, and expansion rate of the universe during its first few minutes. When astronomers measure the amounts of deuterium and helium in environments that have been only minimally altered by later generations of stars, the results agree remarkably well with those predictions. The cosmic microwave background provides another source of information. Its extremely small temperature variations reflect the state of matter when the universe was about 380,000 years old. By analyzing the pattern of those variations, scientists can estimate the amounts of ordinary matter, dark matter, and other components in the universe. Although the background radiation is not a direct inventory of individual elements, it helps define the initial conditions that chemical models must follow. Astronomers also search for ancient stars in the halo of the Milky Way and in nearby dwarf galaxies. Some of these stars contain extraordinarily low amounts of iron and other heavy elements, suggesting that they formed from gas enriched by only one or a few earlier generations of stars. They are not themselves the very first stars, because even they contain small traces of heavy elements, but their compositions resemble ancient chemical records, preserving evidence of the explosions and stellar generations that existed before the Milky Way became the galaxy we know today. Through all these methods, a picture gradually comes into view. The universe was not born with a complete periodic table. It began with a very limited set of ingredients and had to create the rest across many generations. The carbon in living cells, the oxygen in water, the silicon in stone, and the iron in planetary cores were not gifts present from the beginning. They are products of a long history in which matter repeatedly passed through stars, was transformed, and then returned to space. Perhaps this is the most important idea to carry with us when looking back at the age before dust. The early universe was not simply an empty version of the modern one, waiting for planets and life to be placed inside it. It was a place with genuine chemical limits. Those limits determined which kinds of structures could form, how far gas could cool, and how massive the first stars might become. Before the universe could build a solid world, it first had to move beyond the limitations of its original composition. For a very long time, all the matter that might one day become a grain of sand still existed in simpler forms. Silicon was not yet present to bond with oxygen. Carbon had not yet been created in significant quantities. Iron rested in no planetary core, because the first iron atoms themselves had not yet appeared. The universe could expand, gas could move, and gravity could gather matter into enormous clouds, but the ability to build a solid surface still lay beyond what nature could accomplish at that time. Then, within some of the densest regions of gas, collapse began to accelerate. As a cloud was compressed, the temperature at its center rose. Matter continued falling inward, pressure increased, and a young object began forming in the darkness. It was not yet a star in the full sense of the word, but gravity had brought the gas close to the moment when hydrogen nuclei could begin joining together. After hundreds of millions of years filled only with primordial gas and invisible gravitational wells, the first points of light were preparing to appear. Their glow would mark the end of the cosmic dark ages, but the deeper significance lay in what was happening behind that light. Inside the cores of the first stars, the universe would begin doing what the Big Bang had not been able to complete, creating heavier elements from the light ingredients with which it began. From that moment onward, the history of matter would change. Hydrogen and helium would no longer remain almost the only ingredients. Carbon, oxygen, silicon, and many other elements would gradually emerge within the hottest furnaces nature had ever created. The universe still had no dust, but for the first time, it was about to produce the atoms that might one day become dust, stone, and worlds with solid ground. Within the densest regions of gas in the young universe, gravity worked for millions of years without producing any light. Hydrogen and helium slowly fell into regions where dark matter created a stronger gravitational pull, colliding, gradually losing some of their chaotic motion, and gathering into ever larger clouds. At first, the change was almost impossible to notice. One region of space was only slightly denser than its surroundings, but that small difference amplified itself as more matter continued to fall inward. Over time, the center of the cloud became denser, hotter, and increasingly unable to escape its own gravity. There was no dust to shield the inner layers of gas, nor were there carbon, oxygen, or other heavy elements to help the material radiate energy efficiently. Most of the cloud's ability to cool depended on hydrogen, especially the small amount of molecular hydrogen formed through slow reactions in the primordial gas. These molecules could absorb energy from collisions and release it as radiation, allowing the gas to cool enough to continue contracting. Even so, cooling remained far less efficient than it is within the star-forming clouds of the modern universe, where dust and a wide range of heavy elements provide many additional pathways for energy to escape. That difference may have profile. For this reason, some models suggest that primordial clouds tended to produce large concentrations of matter, giving rise to many stars more massive than the Sunday. Such stars would have been hotter, brighter, and faster at consuming their fuel. Yet this picture is far from complete. Increasingly detailed simulations show that disks of gas surrounding the first protostars could still fragment, creating multiple objects with different masses, and there is no firm reason to conclude that every first-generation star was a giant. Astronomers refer to this hypothetical generation as population 3, even though, chronologically, these would have been the first stars. The somewhat backward name comes from the history of astronomical research. Astronomers originally classified nearby stars as population 1, which are rich in heavy elements like the Sun, and population 2, which are older and poorer in heavy elements. They later realized that an even earlier generation must once have existed, formed from matter that had undergone almost no chemical enrichment by previous stars. This generation, which has not yet been directly observed with certainty, became known as population 3. So far, we have not been able to point to a single source of light and say with complete confidence that it is an intact population 3 star. The first stars were born far too deep in the past, and if most of them were massive, they may have lived for only a very short time on cosmic scales. The light from an individual star at such a distance would also be too faint to separate easily from the glow of the galaxy or star cluster forming around it. Our understanding therefore comes from a combination of nuclear physics, computer models, chemical traces preserved in ancient stars, and observations of extremely distant galaxies. Although many details remain unresolved, one conclusion is nearly certain. The first stars must have formed mainly from hydrogen and helium. There were no earlier generations of stars to supply carbon, silicon, or iron to the clouds that created them. They were stars born from primordial matter, and within them, the first major chemical transformation since the opening minutes after the Big Bang was about to begin. As the center of a cloud contracted, its density and temperature continued to rise. Matter falling in from the outside formed a protostar, a body of gas that had not yet established stable nuclear fusion, but had already begun to glow as gravitational energy was converted into heat. Each new layer of infalling gas compressed the center more strongly. Eventually, the temperature in the core became high enough for hydrogen nuclei to approach one another, despite the electrical repulsion between them. Under ordinary conditions, two positively charged nuclei repel each other. Inside a stellar core, immense temperatures and pressures cause the particles to move rapidly enough, while quantum mechanics allows some of them to pass through a barrier that classical physics would consider impossible to cross. As hydrogen nuclei begin to combine and ultimately form helium, a very small amount of mass is converted into energy. That energy moves outward, increasing the internal pressure and resisting the gravity attempting to pull the entire star into collapse. This is the moment when a true star is born. It does not shine because it is burning in the way a flame on Earth consumes fuel and oxygen. There is no chemical fire inside a star. Its light comes from nuclear reactions in which the structures of atomic nuclei themselves are altered. A process unfolding within a relatively small core can sustain the light of a star for millions, billions, or even longer, depending on its mass and the rate at which it uses its fuel. For the first stars, this moment meant far more than the illumination of the cosmic darkness. For the first time since the Big Bang, nature possessed furnaces hot and dense enough to create elements that the early universe had been unable to produce in significant quantities. The Big Bang formed hydrogen, helium, and a very small amount of lithium, but expansion and cooling occurred too quickly for the construction of heavier nuclei to continue. Stars created a new environment, one in which matter could remain at high temperatures long enough for the periodic table to begin expanding. During most of a star's early life, hydrogen serves as its primary fuel. Chains of reactions transform hydrogen into helium, releasing the energy that allows the star to remain in balance. Gravity pulls matter inward, while the pressure of hot gas and radiation pushes outward. A stable star exists between these two tendencies, neither collapsing completely into itself nor expanding without limit. This balance may last for an extremely long time in smaller stars, but in massive stars, higher core temperatures and faster reaction rates cause the fuel to be consumed much more quickly. This creates a gentle paradox in the lives of stars. The more fuel a star possesses, the shorter its life will often be, because greater mass makes the core hotter and forces nuclear reactions to proceed at a much faster rate. A star tens of times more massive than the Sun does not use its fuel sparingly over billions of years. It consumes hydrogen at a tremendous pace, releases an immense amount of energy, and may complete the main stage of its life in only a few million years. For the young universe, that brief lifespan carried great importance. The first heavy elements did not need to wait billions of years to be created. If some population 3 stars were extremely massive, they could have begun changing the chemical composition of their surroundings only a few million years after their formation. In a universe already hundreds of millions of years old, this was almost an instantaneous transformation. As hydrogen in the core gradually ran out, the structure of the star began to change. The energy source that had kept the core stable weakened, allowing gravity to compress the central region into a smaller volume. This contraction raised the temperature, and if the star was massive enough, the core could reach the conditions required for helium to begin participating in new nuclear reactions. Helium is more difficult to fuse than hydrogen because its nucleus carries a greater positive charge, creating stronger repulsion between particles. But when the temperature rises high enough, 3 helium nuclei can take part in a chain of reactions that produces carbon. This process is commonly called the triple alpha reaction, because a helium-4 nucleus is also known as an alpha particle. For an extremely brief moment, 2 helium nuclei form an unstable state of beryllium, and if a third helium nucleus arrives before that structure decays, carbon can be created. Carbon marks a turning point in the history of matter. It is neither the heaviest element nor the most abundant, but its electron structure allows it to form many different kinds of chemical bonds. In the modern universe, carbon appears in interstellar dust, organic molecules, planetary atmospheres, and every form of life known on Earth. Yet before the first stars, there was almost no carbon available to take part in any of those possibilities. Every one of the earliest carbon atoms had to be assembled inside a star from simpler helium nuclei. Some of that carbon could then combine with helium to form oxygen. In sufficiently massive stars, the core would pass through additional cycles of contraction and heating as each source of fuel was gradually exhausted. Carbon could begin taking part in reactions that produce neon, sodium, magnesium, and other elements. Later stages of neon and oxygen burning could create more silicon, sulfur, and a range of heavier nuclei. Each stage occurred at a higher temperature than the one before it, and usually lasted for a shorter period of time. If we could look inside a massive star near the end of its life, its structure might resemble the layers of an onion. The outermost region would still contain hydrogen. Deeper inside would be a layer that had once burned hydrogen and now held a greater abundance of helium. Farther inward would be shells where helium, carbon, neon, oxygen, and silicon were undergoing, or had already undergone, different nuclear reactions. At the center would lie matter transformed into elements from the iron group. The image of layered shells makes the structure easier to imagine, But a real star is not divided by sharp boundaries like those shown in a textbook illustration. Matter can be mixed by convection, the layers can change over time, and many reactions may occur simultaneously in different regions. Even so, the basic idea remains valid. As a massive star grows older, its interior becomes a layered system in which each region records a different stage of nuclear history. This process cannot continue forever in the same way. Fusing light nuclei into heavier ones releases energy when the final product has a more tightly bound structure. But this energy advantage gradually diminishes as the reactions approach the iron and nickel group. Nuclei in this region have very high binding energy per nucleon, which means they are among the most stable structures in nature. Fusing iron into heavier nuclei no longer releases energy that can support the star. Instead, it requires energy. Iron is therefore not an ash in the ordinary sense, but it marks an important limit to the production of energy through fusion in the core of a massive star. Once a core rich in iron group elements has formed, the star cannot simply begin another stage of fuel burning to resist gravity as it did before. The structure that supported the star through all its earlier phases begins to lose its final source of support. This does not mean that elements heavier than iron do not exist or cannot be created in stars. They can form through other processes, especially neutron capture reactions, in which nuclei absorb neutrons and then undergo radioactive changes. Some of these processes occur in aging stars, some in stellar explosions, and some in even more extreme events, such as neutron star mergers. For the story of the first dust, however, what matters most at this stage is that stars had already created carbon, oxygen, silicon, magnesium, iron, and many of the basic ingredients required for solid matter. We should also avoid the overly simple picture of a single star producing the entire periodic table in sequence, and then releasing every element in equal proportions. Stars of different masses follow different paths through life. A small star like the Sun will never pass through all the fuel-burning stages of a giant star. Some elements are produced in large quantities by low and intermediate mass stars. Others come mainly from massive stars, and the heaviest elements may require rarer and more violent events. The chemical composition of the modern universe is the combined result of many kinds of stars and many generations of stellar evolution, not the product of a single kind of furnace. In the first stars, the initial absence of heavy elements also changed the way energy was transported and the way the stars evolved. Elements such as carbon, nitrogen, and oxygen can act as catalysts in a cycle of reactions that converts hydrogen into helium. In stars that began without those elements, the earliest stages had to rely on other pathways. Only after a small amount of carbon had been created in the core could some of the more efficient reaction cycles begin to contribute. This difference shows that a population 3 star was not simply a modern star with all its heavy elements removed. Its entire internal structure, surface temperature, size, rate of mass loss, and final fate could have been different. Because the surrounding gas contained almost no dust, the star's radiation also interacted with its environment in different ways. High-energy photons could ionize hydrogen across a vast region, creating bubbles of hot gas and beginning to transform the space that had once remained within the cosmic dark ages. The first stars therefore changed the universe in 2 directions at once. Their light began altering the electrical state of the gas between galaxies, contributing to the reionization of the universe. At the same time, deep within their cores, they were building new elements that had not yet escaped into space. One transformation unfolded across thousands of light years around the star, while the other remained confined within a much smaller region, though it would eventually influence the entire history of solid worlds. How can we know what happens inside a distant star when we cannot look directly into its core? Much of our understanding comes from light. When starlight is separated into a spectrum, it contains absorption and emission lines associated with the elements in the star's outer layers. Each element interacts with light at a characteristic set of wavelengths, much like a fingerprint. By reading those fingerprints, astronomers can determine a star's composition, surface temperature, motion, and many other properties. Spectroscopy does not allow us to observe each layer of the core directly, but nuclear physics and models of stellar structure can connect what is seen at the surface with the processes occurring inside. These models are tested against many different kinds of evidence, including stellar masses and luminosities, the ages of star clusters, oscillations on stellar surfaces, and neutrinos created in nuclear reactions. In the case of the Sun, neutrinos provide especially direct evidence that hydrogen fusion is taking place in the core, because these particles escape almost immediately and pass through matter with remarkable ease. For stars that died long ago, the composition of ancient stars from later generations provides another source of information. A low-mass star can survive for tens of billions of years, longer than the current age of the universe. If it formed from a cloud of gas, enriched by only one of the earliest stellar explosions, its atmosphere may preserve distinctive ratios of carbon, magnesium, calcium, iron, and other elements. Astronomers read those ratios as clues, then compare them with models of first-generation stars with different masses and different kinds of endings. Some stars that are extremely poor in iron, but relatively rich in carbon, have made the story more complex. They suggest that the earliest stellar generations did not always distribute elements in the same pattern. One explosion might release large amounts of carbon while trapping most of its iron within a collapsed remnant. A rapidly rotating star might mix its internal layers in a different way. Two stars of similar mass could still leave behind very different chemical signatures, depending on their rotation, internal structure, and the energy of their final explosions. This reminds us that the chemical history of the universe did not unfold along a single, simple path. The periodic table was not filled one box at a time, in a neat sequence, and then left unchanged. Elements appeared in different places, in different amounts, through overlapping processes. One region of gas might become enriched in carbon, while remaining extremely poor in iron, while another received greater amounts of silicon and oxygen. Later generations of stars formed from these uneven mixtures and continued adding new products of their own. Yet no matter how complex the details became, the greatest transition can still be seen clearly. Before the first stars, the universe possessed only a small number of light elements. After those stars passed through their nuclear stages, carbon, oxygen, silicon, and other ingredients had entered the natural world. They still remained deep within stellar layers, held in place by gravity, and unable to become part of a dust cloud or a planet. But the chemical possibilities of the universe had already expanded. A carbon atom created in a stellar core had no knowledge that billions of years later, atoms of the same kind might take part in organic molecules or become part of a living body. A silicon nucleus buried within the deep layers of a giant star carried no image of the grains of sand, planetary crusts, or mountain ranges that would appear in the future. Matter has no purpose and moves toward no predetermined outcome. Even so, as new elements came into existence, the range of possibilities allowed by the laws of nature became wider. At this stage, the universe still did not contain dust in the full sense of the word. Interstellar space remained composed mainly of hydrogen and helium. The ingredients needed for the first solid grains were still locked inside stars, like minerals held deep within a furnace that had not yet opened. Before carbon, silicon, oxygen, and iron could take part in the history of planets, they first had to escape the temperatures and pressures in which they were created. For smaller stars, the return of matter to space could unfold gradually during the final stages of their lives. But for many massive stars, the process would be faster and far more violent. As their cores approached the iron group and could no longer produce enough energy to resist gravity, the balance that had sustained them throughout their lives would begin to fail. The central region would collapse, while the outer layers prepared to undergo an event capable of launching newly formed elements into space. The first stars illuminated the universe, but their light was not the most enduring gift they left behind. Their deeper legacy lay in the atoms created beneath their brilliant surfaces, where hydrogen and helium had been transformed into a richer collection of elements. Only when stars began returning those atoms to the darkness between galaxies could the story of the first dust grains truly begin. Carbon, oxygen, silicon, and iron had already appeared in the universe, but for a long time they remained trapped deep inside stars. Their temperatures were so high that atoms collided constantly. Electrons could be stripped from their nuclei, and no solid structure had any chance of surviving. A star could quietly create new elements for millions of years, while the space around it remained composed almost entirely of hydrogen and helium, if the material within had not yet found a way to escape. The history of dust therefore entered a new stage. The universe had created the necessary ingredients, but now it had to release them from the furnaces in which they were born. Throughout most of a massive star's life, gravity and pressure maintained a balance that was always slowly changing. Gravity pulled every layer of matter toward the center, while energy produced by nuclear reactions kept those layers from collapsing. Each time one kind of fuel began to run out, the core contracted, heated up, and opened the way to a new stage of reactions. This sequence continued through hydrogen, helium, carbon, neon, oxygen, and silicon. But it could not continue forever. Once the center became rich in iron group elements, the star approached a limit beyond which fusion could no longer provide energy in the same way. The mass of the core continued to grow as the outer layers fed the products of nuclear reactions inward. Matter was compressed to extraordinary densities, while electrons contributed pressure that resisted further contraction. Beyond a certain threshold, that structure could no longer support its own weight. High-energy photons began breaking apart some nuclei, drawing away thermal energy that was needed to maintain pressure. At the same time, electrons were forced into protons, creating neutrons and releasing enormous floods of neutrinos. Within a few brief moments, the core that had remained stable for millions of years began to collapse. The speed of this event was almost impossible to compare with the star's long lifetime. The core could contract in only a fraction of a minute until matter reached a density close to that found inside atomic nuclei. Neutrons were forced tightly together and resisted further compression, causing the collapse to slow abruptly. A shock wave formed and began moving through the layers of matter still falling inward. Neutrinos pouring from the newly formed core transferred additional energy to the surrounding material, helping drive it outward. From a great distance, the star suddenly became a brilliant point of light. A supernova can outshine billions of stars in its galaxy. But the most important part of the event for this story was unfolding beneath that radiance. Carbon, oxygen, magnesium, silicon, sulfur, calcium, and many other elements were hurled out of the star at tremendous speeds. Layers that had once been buried far below the surface now expanded into space, carrying chemical ingredients the primordial universe had never possessed. The explosion also created new material. The shock wave heated the stellar layers for a brief period, triggering nuclear reactions that could not have been sustained during the star's earlier, stable phases. Many isotopes formed during these final seconds, including radioactive isotopes that continued to decay after the material had left the star. A supernova, therefore, both released elements created throughout the star's lifetime and completed additional nucleosynthesis in the very moment the star was torn apart. The material did not spread outward as a perfect sphere with a uniform composition. Within the expanding cloud were layers, filaments, and knots of matter with different densities. Some regions were rich in oxygen, while others contained more silicon or iron. Different clumps moved at different speeds, reflecting the complex structure of the star before the explosion and the asymmetry of the collapse itself. As this cloud collided with interstellar gas, it formed a supernova remnant that could continue expanding for tens of thousands of years. The newly released elements did not immediately mix evenly throughout an entire galaxy. One explosion could strongly enrich a relatively small region, while areas not far away retained almost the same composition they had before. Later generations of stars would carry the imprint of this uneven mixing. One cloud might contain abundant carbon but little iron. Another might receive more oxygen, magnesium, or silicon. The composition of each ancient star therefore resembles a local record of the events that occurred before its birth, rather than a copy of one universal mixture spread evenly across the cosmos. The way a star died determined how much material was truly released. Two stars might create similar elements in their cores and yet leave very different legacies. If an explosion was powerful enough, many layers of matter could escape the star's gravity and enter interstellar space. If the energy was weaker, some of the material could fall back onto the central remnant. Iron and other heavy elements buried in the deepest layers might remain trapped inside a neutron star or black hole, leaving the surrounding space with less than the star had actually produced. Some very massive stars may have collapsed almost directly into black holes, ejecting only a small portion of their material. In such cases, an enormous stellar furnace could operate for millions of years and leave behind very little chemical evidence for later generations. Other stars may have produced explosions powerful enough to destroy nearly their entire structure. The boundaries between these outcomes depended on the star's mass, rotation, mass loss, and internal structure, all of which remain active areas of research for population 3 stars. Within a particular range of masses, models predict the possibility of a pair instability supernova. Temperatures in the core of an extremely massive star can become so high that energetic photons transform into pairs of electrons and positrons. Radiation pressure drops as energy is diverted into creating particles, causing the core to contract and its temperature to rise rapidly. Nuclear fuel then ignites in a reaction powerful enough to destroy the entire star, leaving behind neither a neutron star nor a black hole and releasing a vast quantity of heavy elements. Such explosions are especially compelling in studies of the early universe, because population 3 stars may have reached extremely high masses. Even so, they cannot yet be regarded as a common fate of the first stars. Astronomers are still searching for the distinctive elemental patterns that a pair instability explosion might have left behind in ancient stars. Several possible signs have been proposed, but the evidence is not yet clear enough to determine how much these events contributed to the earliest chemical enrichment. Supernovae returned material to space quickly, but the universe also had slower pathways. Low and intermediate mass stars did not develop iron cores large enough to collapse like those of massive stars. Near the ends of their lives, they expanded into red giants and later entered the asymptotic giant branch, commonly known as the AGB phase. By then, the stellar core had become dense, while the outer layers had expanded to great distances and were held only loosely by gravity. The hydrogen and helium-burning shells around the core did not operate with perfect regularity. Periodic thermal pulses could stir the interior strongly, carrying carbon and other products of nuclear reactions closer to the surface. The composition of the outer gas gradually changed with each episode. When carbon became more abundant than oxygen, the star could become a carbon star, surrounded by an atmosphere rich in carbon-bearing molecules, and by conditions favorable for certain kinds of solid grains to form farther from the hot surface. AGB stars lost matter through winds that continued for thousands of years. Their surfaces pulsed, layers of gas were repeatedly lifted and allowed to cool, and radiation pressure transferred momentum to tiny particles forming within the expanding atmosphere. The material left the star far more slowly than ejecta from a supernova, creating widening shells around the gradually exposed core. Carbon and many other elements entered space through a process that was not especially sudden, but lasted long enough for the total amount of released material to become substantial. These sources of matter appeared on different timescales. Massive stars lived for only a few million years, allowing them to enrich their surroundings during the earliest stages of a galaxy's history. AGB stars required more time to evolve, from tens of millions of years for relatively massive ones to billions of years for smaller stars. In a newly forming galaxy, supernovae could contribute first. As more generations of stars were born and aged, AGB winds began adding further carbon, nitrogen, and dust to the interstellar medium. Massive stars could also lose material before they exploded. Their intense radiation drove the outer gas into stellar winds, sometimes carrying away a large fraction of the star's original mass. In modern stars rich in heavy elements, metal ions absorb light and help accelerate those winds. Population 3 stars began with almost none of these elements, so their rates of mass loss may have been lower. Rapid rotation, surface instabilities, and interactions within binary systems could still have expelled material, but their exact contribution remains uncertain. All of these streams of matter eventually met in interstellar space. Gas from supernovae rich in oxygen and silicon could mix with carbon released by AGB stars. Primordial hydrogen and helium still made up most of the mass, but heavy elements began exerting an influence far greater than their small abundance might suggest. Clouds of gas now had more ways to radiate energy and cool. Chemistry also became more varied, as atoms could combine into molecules that could never have existed in the primordial universe. The matter returned by stars did not remain motionless in space forever. Expanding streams of gas gradually slowed, cooled, and blended into larger clouds. Gravity continued, gathering them into new regions of greater density, where later generations of stars could be born. Each generation formed from the hydrogen and helium left over from the beginning, mixed with the products of stars that had lived before. Through many such cycles, the abundance of heavy elements slowly increased. Although the rate of enrichment varied greatly from one galaxy to another, and even between different regions of the same galaxy, the universe could no longer return to its completely primordial state. Once carbon, oxygen, and silicon had been released into space, they became part of a much larger cycle of matter. Some atoms were drawn into new stars and passed through further nuclear reactions. Some wandered among interstellar clouds for long periods. Others began participating in the chemistry that would eventually produce the first molecules and solid grains. Light allows astronomers to follow this process from enormous distances. The spectrum of a supernova changes over time as its expanding layers become more transparent. The earliest days may reveal hydrogen or helium in the outer regions, while later stages expose oxygen, silicon, calcium, and iron from deeper layers. The width of the spectral lines reveals how quickly the material is moving, while changes in brightness help estimate the energy of the explosion and the amount of radioactive material that was created. Some supernovae continue glowing for months because nickel 5-6 decays into cobalt 5-6 and then into iron 5-6. The energy released through this chain of decay heats the ejected material and sustains the light long after the initial explosion has passed. The light curve becomes an indirect measurement of how much nickel was produced, offering clues to what occurred within the deepest layers of the star. Nearby supernova remnants allow this story to be observed in greater detail. X-ray, infrared, and radio telescopes can map regions enriched in different elements. Iron is sometimes found in clumps that have traveled farther than expected, while oxygen and silicon form intricate filaments. These structures show that the explosion mixed the star's layers in ways that were not perfectly symmetrical, creating regions with very different chemical conditions and temperatures. The traces of AGB stars appear in the expanding shells of gas around them and in the planetary nebulae, formed after their outer layers have left the star. The name planetary nebula comes from the round, planet-like appearance these objects had through early telescopes, not because they produce planets. Their spectra reveal carbon, nitrogen, oxygen, and many other elements being returned to the interstellar medium. Some evidence has even survived as physical matter. Within primitive meteorites, scientists have discovered microscopic grains whose isotope ratios differ clearly from those of most material in the solar system. They are known as Pressler grains because they formed before the Sun and planets came into existence. Their isotopic fingerprints show that some condensed within the winds of AGB stars, some came from supernovae, and others originated in distinct stellar environments. These grains were not the first solid matter in the universe. They formed much later, after the Milky Way had already passed through many generations of stars. Their value lies in the journey they preserve. Matter could form around an aging star, enter interstellar space, survive within a new cloud, and eventually become part of another planetary system. Within a grain smaller than the width of a human hair, the history of a long-dead star can still be recognized billions of years later. At this point, an important boundary must remain clear. The release of carbon, silicon, oxygen, and iron did not mean that dust had already appeared. During the early stages after a supernova, the material was still extremely hot, highly ionized, and moving at tremendous speed. The necessary atoms existed together within the cloud, but they could not yet remain joined in stable bonds. Having the ingredients and having a solid grain are two very different states of matter. The temperature had to fall low enough for the first clusters of atoms to avoid being broken apart immediately after forming. The density also had to remain high enough for collisions to occur before the expanding gas became too thin. Chemical composition determined which kinds of bonds could appear. Carbon could form carbon-rich dust if it was not entirely locked into carbon monoxide. Silicon, oxygen, magnesium, and iron could take part in silicates or oxides when the proportions and conditions were right. Even a small change in the environment could lead to an entirely different kind of dust. The newborn grains also had to face the environment that had created them. As supernova ejecta rushed into the surrounding gas, one shock wave moved outward while a reverse shock traveled back through the expelled material. The gas was heated once again. Fast-moving ions struck the surfaces of the grains and eroded them atom by atom. Small grains could be destroyed completely, while larger grains, or those sheltered within dense knots of matter, had a better chance of surviving. A supernova could therefore play three roles that seem almost contradictory. It produced the elements needed for dust, created conditions in which some of that material could condense into grains, and then carried those same grains through shock waves capable of destroying them. The amount of dust observed in a young remnant was not necessarily the amount that would eventually enter interstellar space. The surviving fraction depended on grain size, composition, the structure of the remnant, and the density of the gas encountered by the shock wave. Around AGB stars, the process unfolded at a different pace. Gas was lifted away from the hot surface and moved outward, where the temperature gradually fell while the density remained high enough for chemistry to continue. The first stable molecular clusters could become condensation seeds. Additional atoms attached to their surfaces, allowing the grains to grow. Starlight transferred momentum to the dust, while the grains dragged the surrounding gas with them and helped sustain the wind-carrying material away. Here, dust was not only a product of the outflow, but also part of the mechanism that allowed the star's outer layers to keep escaping. After millions of years in which only primordial gas had existed, the universe had finally entered an entirely new state. The elements needed to form rock were no longer confined within stellar cores. They had entered space, mixed with clouds of hydrogen and helium, and begun participating in more complex chemistry. Even so, most matter still existed as atoms, ions, or molecules within gas. The ingredients of stone were present, but stone itself had not yet appeared. Within the cooling layers of matter, extremely small clusters of atoms began to form and then disappear. Most did not survive long enough to become anything larger. A few reached stable arrangements, continued collecting atoms from their surroundings, and crossed the fragile boundary between gas and solid matter. No brilliant flash marked this transition. One of the first dust grains may have appeared in silence, far too small to be seen, within the fading material of a dead star. Stars had completed the first two stages of the journey. They created the elements the Big Bang could not produce, and then returned those elements to space. The next stage unfolded on a far smaller scale, where temperature, density, and chemical bonding determined whether a group of atoms would fall apart or become a stable solid grain. The universe now possessed the ingredients for dust, but every newborn particle still had to find a way to survive within an environment capable of destroying it at any moment. Within the expanding material surrounding a dead star, the temperature continued to fall with each passing day, month, and year. Atoms that had once been ionized in the extreme heat began regaining their electrons. Simple molecules appeared wherever the gas remained dense enough, and collisions that had previously produced only chaos now began opening the possibility of chemical bonds. There was no bright, distinct boundary marking the moment. The transition unfolded across scales far smaller than any astronomical image could reveal, as a few atoms happened to meet, held together long enough, and formed a structure that did not immediately fall apart. This was the point at which the story of the elements became the story of dust. An atom of silicon, carbon, or iron could remain in a gas for thousands of years without ever becoming part of a solid. To cross that boundary, it had to join a chain of chemical bonds strong enough to resist the thermal motion trying to pull its components apart. The higher the temperature, the faster the particles moved, and the more easily small clusters were destroyed. As the gas cooled, that motion gradually slowed, allowing some bonds to survive for longer periods. Density was equally important, because if the atoms were too widely separated, the gas would expand and thin out before enough collisions could occur. In simple descriptions, dust is often said to condense directly from gas, in much the same way that water vapor forms droplets on a cold surface. That comparison is only broadly accurate. The space around a star contains no ready-made surface for matter to settle onto. The first grains had to create their own starting points by forming clusters stable enough for additional atoms to attach. This process is known as nucleation, and it is one of the most difficult stages in the entire history of dust to describe. A cluster containing only 2 or 3 atoms is usually extremely fragile. It may survive for only a brief instant, collide with another particle and break apart, or be destroyed by a photon carrying enough energy. Once the cluster reaches a certain size, its structure becomes more stable, and its chances of survival increase. From that point forward, growth can proceed more quickly, because each new atom no longer has to find another tiny group within the gas. It only needs to strike a surface that already exists. The dust grain begins increasing in size by collecting material from its surroundings. Not every cooling region of gas produces the same kind of grain. Chemical composition determines which bonds are likely to form, and the ratio of carbon to oxygen is especially important. Carbon and oxygen readily combine to form carbon monoxide, a relatively stable molecule. If oxygen is more abundant than carbon, very little free carbon may remain, while the excess oxygen continues bonding with silicon, magnesium, and iron to form oxides or silicate structures. When carbon is more abundant than oxygen, some carbon remains outside carbon monoxide and can participate in the formation of carbon-rich clusters, opening the way to carbon dust and silicon carbide. Silicate is a general name for a very broad family of materials, not a single compound with the same structure everywhere. Many silicate grains contain silicon and oxygen combined with magnesium, iron, or other elements. Some have relatively ordered crystalline structures, while many grains in space exist in an amorphous form, where the atoms are not arranged in a regular, repeating network. These differences depend on the rate of cooling, the temperature at which the grain formed, and the thermal history it experienced afterward. Carbon dust also exists in more than one form. Carbon can create amorphous structures, soot-like particles, large ring-shaped molecules, or more ordered networks under suitable conditions. Silicon carbide forms when silicon bonds with carbon in a carbon-rich environment. Presolar grains found in meteorites have shown that silicon carbide can truly condense around aging stars and survive a long journey through interstellar space. They were not the first grains in the universe, but their structure and composition help scientists test models of condensation within stellar gas. Oxides may form before certain silicates, because simple compounds containing oxygen and metals can become the first seeds on which other materials later grow. Aluminum oxide is one example often studied in the atmospheres of aging stars, where it may condense at relatively high temperatures and survive much closer to the star than many other forms of dust. Farther away, after the gas has cooled further, silicates or other materials may collect on those existing seeds. A grain, then, does not necessarily have the same composition from its center to its surface. Its tiny structure may preserve several different stages of growth. Iron presents a more complicated story. It may be incorporated into silicate structures, form oxides or sulfides, or exist as metallic iron under certain conditions. Its ability to condense depends strongly on the chemical environment and the cooling rate. In galaxies, poor in heavy elements, where silicon and magnesium are scarce, iron may take part in pathways of dust formation that differ from those familiar in the Milky Way. Modern observations are gradually revealing that solid matter does not have to form according to a single formula, even when the available ingredients are extremely limited. Cosmic dust must be clearly distinguished from the dust of everyday life. Some household dust consists of fabric fibers, pollen, flakes of skin, soil, or material worn away from larger objects. Primordial cosmic dust did not begin with the breaking apart of rocks, because no rocks yet existed. The first grains were built directly from gas, one atom or molecule at a time. They were more like newly condensing crystals, or freshly formed particles of soot than fragments shed from a planet. Their sizes were also far smaller than we usually imagine. Many interstellar dust grains measure only a few thousandths to a few tenths of a micrometer across, hundreds or thousands of times narrower than a human hair. A single grain contributes almost nothing in terms of mass. But when countless grains fill a cloud stretching across many light years, their combined influence becomes immense. They absorb light, scatter photons, emit infrared radiation, and provide surfaces on which chemical reactions can occur. The first grains may have condensed within supernova ejecta, in the winds of aging stars, or in other dense regions of gas surrounding stars. Each environment followed its own timescale. In the winds of AGB stars, gas moved away from the surface relatively slowly, cooled gradually with increasing distance, and could maintain suitable densities across a wide region. Supernova ejecta expanded much more rapidly, causing conditions to change dramatically with time. Grains had to form after the gas had become cool enough, but before its density fell too low for further growth to continue. Scientists once debated whether supernovae mainly created dust or destroyed it. The present answer does not fall entirely on either side. Infrared observations show that dust can appear within the ejecta only a few hundred days after an explosion. In somewhat older remnants, the amount of cold dust is sometimes far greater than early estimates suggested, indicating that some grains may form later or simply become easier to detect as their temperatures fall. The same event that creates an environment for condensation also produces shock waves capable of eroding the grains. A grain newly formed inside a supernova remnant does not immediately enter a quiet region of space. The ejecta are still rushing outward at tremendous speed. When they strike the interstellar gas, a forward shock heats the surrounding environment, while a reverse shock travels back into the expelled material. The temperature around the grain rises once again. High-energy ions repeatedly strike its surface and knock away individual atoms, a process commonly known as sputtering, or erosion through particle collisions. The rate of destruction depends on the size of the grain. In a small grain, most of the material lies close to the surface, so losing even a thin outer layer may be enough to erase it completely. Larger grains contain more material within their interiors and have a better chance of surviving. Composition also makes a difference, because different kinds of chemical bonds do not resist heat and collisions equally well. The density of the gas surrounding a grain determines how often it is struck, while a location inside a dense knot of material may provide some degree of protection from the hot environment beyond. There is no single survival rate that applies to every supernova. One model may predict that most dust will be destroyed in a dense environment, while a structure filled with knots and filaments may allow a significant amount to escape. Grains are distributed unevenly, shock waves are not perfectly symmetrical, and magnetic fields can make their paths even more complex. This diversity makes it difficult to translate the amount of dust observed in a young remnant into the amount that will truly enter the interstellar medium. A grain that survives the shock wave has still not completed its journey. It begins traveling through the interstellar medium, where hot, warm, and cold regions are woven together. In thin, hot gas, the grain continues to face radiation and collisions. When it enters a colder cloud, its surface may collect additional atoms and molecules. In this way, a grain is not created only once. Its original core may form around a star, while much of its later mass is added within interstellar clouds. This is an important part of the story, because the amount of dust observed in some galaxies is sometimes greater than stellar sources alone could have supplied within the available time. AGB stars and supernovae create dust seeds, along with part of their initial mass. When those grains enter cold, dense gas, elements that remain in the gaseous state attach to their surfaces and build new layers. A silicon atom does not need to create a seed from the beginning if a carbon or oxide grain is already present for it to strike. Growth on an existing surface is far more efficient than repeatedly forming new clusters directly from the gas. Higher density shortens the distance between collisions. Lower temperatures allow atoms to remain attached for longer instead of immediately bouncing away from the surface. Layers of ice made from water, carbon monoxide, carbon dioxide, methane, ammonia, and other molecules can coat grains inside cold clouds. These icy mantles do not necessarily last forever. When a grain approaches a new star, or is heated by radiation, volatile molecules return to the gaseous state. The more durable solid core may survive and continue through another cycle. A dust grain can therefore carry a history written in layers. Its center may have formed in the gas surrounding an aging star. Its surface may continue growing inside a molecular cloud. An icy coating may appear as the temperature falls. Radiation from a young star may remove that ice and expose the material beneath it. Collisions with other grains may alter its structure, while a later shock wave may erode much of its outer surface. What we describe with the simple word dust is actually a collection of matter that is continually being built, broken apart, and rebuilt. The ability to grow within the interstellar medium helps explain how dust could become widespread, even if the earliest stars supplied only a limited number of seeds. The universe did not require every heavy atom to condense directly within a stellar wind or supernova. As long as enough grains survived to carry the first surfaces into cold clouds, the remaining material could be added gradually. In this sense, stars created the seeds, while the darkness between them completed a large part of their structure. The contribution from each source is not the same in every galaxy and has not yet been determined with equal certainty. In very young systems, there may not have been enough time for many low-mass stars to reach the AGB phase, allowing supernovae and rapid grain growth inside clouds to play more prominent roles. In galaxies with longer histories of star formation, AGB winds contribute substantial amounts of carbon and other forms of dust. Gas density, radiation intensity, supernova frequency, and the abundance of heavy elements all shift the balance between formation, growth, and destruction. A galaxy does not preserve a fixed amount of dust. Each generation of stars adds new solid material, but stellar explosions also destroy grains that already exist. Some dust is drawn into new stars and completely vaporized by the temperatures within them. Some enters protoplanetary disks, where grains collide and become larger objects. Other particles are driven out of the galaxy by winds and radiation. The amount of dust observed at any one moment is the temporary result of many opposing flows, not simply the total quantity that has ever been created. Light is the primary tool for tracing grains too small to observe individually. Dust near a hot source absorbs high-energy photons and becomes warmer. It then releases that energy again, mainly at infrared wavelengths. From the shape of the emission spectrum, astronomers can estimate the temperature and quantity of the dust. Broad spectral features can also reveal its approximate composition, including signatures associated with silicates or silicon carbide. Estimating dust mass is not entirely straightforward. The same infrared brightness may be produced by a small amount of hot dust or a much larger amount of colder material. Grain shape and size affect the way light is absorbed. Uncertainty about composition creates uncertainty in emissivity. The coldest grains usually radiate at longer wavelengths, requiring telescopes and instruments different from those used for near-infrared observations. Measurements across many wavelength ranges must be combined to reduce these ambiguities. Spectroscopy can also reveal when molecules begin forming before the dust itself. Carbon monoxide, silicon monoxide, and many other molecules have been observed within supernova ejecta. Their appearance and later decline help trace the progress of the chemistry. If silicon monoxide becomes less abundant while the signal from silicate dust grows stronger, scientists may interpret this as evidence that some silicon is leaving the gaseous phase and entering solid material. Conclusions like these usually depend on several layers of evidence rather than a single observation. Pre-solar grains provide additional information on a laboratory scale. The isotope ratios of carbon, nitrogen, silicon, oxygen, and other elements can identify the kinds of stars in which they formed. Microscopes reveal the shapes of their surfaces, while highly precise analytical methods measure the composition of tiny individual regions. Some grains contain distinct cores and outer coatings, preserving evidence of several stages of growth. These samples demonstrate that stardust can survive the interstellar medium and enter a new planetary system without being completely mixed at the atomic level. Despite all this evidence, the exact moment when the first dust grain appeared remains beyond our ability to determine. The earliest stars may have created heavy elements and expelled them only a few million years after they began to shine. Dust may have condensed within that material soon afterward. The interval between the first stars and the first solid grains was probably very brief compared with the age of the universe, but we do not yet have evidence direct enough to assign it to one precise moment. The first dust grains probably formed too far away and too early for us to see them individually. Most were heated, shattered, or drawn into later generations of stars. Even grains that still exist in nearby galaxies are so small that no telescope can magnify them into clearly shaped objects. They do not appear as points of light against the sky, because dust itself is usually too cold and too faint to emit the kind of light the human eye can see. Even so, dust is not completely silent. Every tiny grain interacts with the light passing through it, and when countless grains lie along the same line of sight, their combined effect becomes large enough to measure. Astronomers do not need to see each grain directly. They observe a star growing dimmer, a region of the sky becoming darker, or energy appearing where it was not expected. Through changes like these, the presence of dust gradually reveals itself. In visible light, dust often makes itself known by obscuring whatever lies behind it. A cloud may contain thousands of stars, but if enough dust stands between those stars and us, part of the cloud can appear as a dark patch. What looks like an empty opening may actually contain a great deal of matter. The light is still being produced behind it, but it no longer reaches the observer unchanged. The degree of obscuration also varies with color. Blue light is often blocked more strongly by many kinds of dust than red light, causing a star viewed through dust to appear redder than it truly is. By comparing the observed color with the star's temperature and type, astronomers can estimate how much light was lost along the way. Dust does not need to shine brightly on its own. By altering another source of light, it already leaves a measurable trace. The absorbed energy does not disappear. A dust grain that receives light warms slightly, then releases that energy back into space as infrared radiation. This light has wavelengths longer than those visible to the human eye. A region that appears dark in an ordinary image may become bright when observed with an infrared telescope, as though the material that once concealed itself were quietly returning the very energy it had taken from starlight. This transformation allows us to trace dust through places that seem almost empty. Dust near a hot star receives more energy and produces a stronger signal. Dust buried deep inside a cold cloud emits more weakly and at longer wavelengths. By combining many measurements, scientists can estimate how much dust a region contains and its approximate temperature, although those values still depend on the kinds of grains present. A small amount of warm dust can sometimes produce nearly the same brightness as a much larger amount of colder dust. Grains with different compositions also absorb light in different ways. For that reason, seeing an infrared glow tells us only that solid material is likely present. To understand what it is made of, the light must be separated in greater detail. When light passes through a prism or a similar instrument, it is spread into a range of wavelengths known as a spectrum. Certain materials absorb or emit energy more strongly in particular regions, creating characteristic curves and dips. These features are not always as clear as a signature written in advance, but they are distinct enough to compare with laboratory samples and theoretical models. Silicates leave a different kind of signal from carbon-rich dust. A compound made from silicon and carbon may appear in another part of the spectrum. Some kinds of dust produce relatively recognizable features, while others alter the overall shape of the spectrum only slightly. Astronomers must test many possibilities, identify which mixture best reproduces the data, and then ask whether that solution also fits the star and its surrounding environment. This way of reading light transformed dust from an obstacle into a source of information. For a long time, astronomers mainly tried to remove the effects of dust from their data so they could see the stars behind it more clearly. As infrared instruments became more sensitive, that obscuring veil began to be studied as an important part of the universe itself. Dust does more than block light. It preserves information about the stars that created it, the clouds through which it traveled, and the chemical conditions inside its galaxy. The James Webb Space Telescope is especially well suited to this search because most of its observations are made in infrared wavelengths. Rather than looking only at stars shining intensely, Webb can detect weaker energy from cooler material and see through some regions that dust obscures in visible light. Its ability to collect highly sensitive spectra also allows it to distinguish extremely subtle changes in the light passing through layers of matter around aging stars. Very distant galaxies offer a direct view of the universe when it was still young, but their distance causes the light from many stars and clouds to blend together. A telescope may reveal that dust was present in an early galaxy, while determining which stars created it or which grain type dominated remains extremely difficult. To understand what may be happening inside those distant points of light, scientists turn to several nearby galaxies whose chemical composition is still relatively simple. One such place is called Sextans A. It is a small dwarf galaxy located about 4 million light-years from the Milky Way. That distance is still enormous by any everyday measure, but it is close enough for Webb to observe individual aging stars rather than seeing only a blended glow from the galaxy as a whole. Sextans A is not a perfectly preserved fragment of the primordial universe. It has formed stars over a long period and has been enriched by many stellar generations. What makes it unusual is that its abundance of heavy elements remains only a small fraction of that found near the Sunday. Ingredients such as silicon, magnesium, and iron are relatively scarce, forcing dust formation to occur under conditions closer to those that may have existed in young galaxies. In this sense, the galaxy resembles a kitchen with very few ingredients. We cannot say that everything produced there is identical to the matter of the early universe, but observing how stars adapt to such scarcity can reveal the pathways through which dust may have appeared at very early times. Webb focused on a group of stars that had entered the final stages of their lives. These stars were gradually losing their outer layers, returning material created inside them to space. In the Milky Way, similar aging stars often form familiar shells of dust. If the surrounding gas contains abundant oxygen, silicon, and magnesium, silicate grains can condense as the material moves away from the hot surface and cools. In Sextans A, the low amounts of silicon and magnesium led scientists to predict that some aging stars might be almost unable to produce much dust. A star could still expel gas, but that outflow would lack the ingredients normally used to build silicate grains. Webb's data, however, showed that the story did not end with this simple shortage. Around one of the observed stars, the infrared light did not carry the strong silicate signature that might have been expected. Instead, it showed a smoother form, more similar to the kind of signal that iron-rich grains could produce. When scientists tried to reproduce the data using different mixtures of material, the best-fitting solution involved a dust shell containing almost no silicate and possibly composed largely of iron. This was not a sample of iron grains collected and examined directly. The conclusion was built from the way light changed as it passed through the material around the star. The most precise statement is that the data are more consistent with iron-rich dust than with the more familiar mixtures that were tested. That caution matters, because a smooth signal is often more difficult to identify than one produced by a material with a prominent spectral feature. The importance of the result does not lie in iron being an entirely new ingredient in dust. What is surprising is that it may become a dominant component around a star living in an environment poor in heavy elements. When silicon and magnesium are too scarce to produce much silicate, the star does not necessarily stop creating solid matter. Another pathway may become more important, using whatever material is still able to condense. Another star in the same survey revealed a signature of silicon carbide, a material made from silicon and carbon. This star was carbon-rich because it had carried carbon from its interior into its outer atmosphere. Carbon can be produced by the star itself, so it does not depend entirely on the chemically poor cloud from which the star was born. Silicon remains scarce, but even a small amount, taking part in condensation, was enough to create a feature Webb could detect. The two stars told different stories. In one case, iron-rich dust may be favored when the familiar ingredients for silicates are in short supply. In the other, a small amount of silicon combines with carbon produced by the star itself. Together, they show that a galaxy poor in heavy elements does not simply create a smaller quantity of the same dust mixture found in the Milky Way. The composition of its dust may change in response to the scarcity of its environment. This is especially important when studying distant galaxies. If scientists always assume that dust in the young universe resembled the dust near the Sun, they may misinterpret the light they receive. Iron-rich dust may not leave a prominent feature like silicate dust does. It can still absorb and re-emit energy, but it may be difficult to recognize if the models are searching only for familiar materials. Some of the solid matter in the earliest galaxies may have been present in forms that were far less obvious. The aging stars of Sextans A also show that this source of dust does not necessarily require billions of years to appear. Stars like the Sun live for a very long time before entering the stage when they shed their outer layers, but more massive stars can pass through their entire life cycles much more quickly. Some sufficiently massive aging stars may begin releasing dust after only a few tens of millions of years, a brief interval compared with the lifetime of a galaxy. Supernovae remain extremely important potential sources of both elements and dust in the young universe. The discovery in Sextans A does not replace that role. Instead, it adds another pathway, showing that relatively fast-evolving aging stars may also contribute solid material earlier than once imagined. The actual contribution will vary from galaxy to galaxy, depending on how many stars are born, their masses, and how successfully the grains survive after leaving their source. Webb's investigation extended beyond the layers of material surrounding stars. The telescope also observed regions between the stars, where dust had already left its birthplace and begun mixing into broader clouds of gas. There, a carbon-related signal appeared in small clusters rather than being spread evenly throughout the galaxy. The source of this signal was a family of carbon structures made from multiple linked rings, commonly known as PAHs. They are larger than most simple molecules but smaller than typical dust grains, occupying the blurred boundary between molecular chemistry and solid matter. When they absorb an energetic photon, they vibrate and release the energy again in several characteristic regions of the infrared spectrum. Before Webb, galaxies with very low abundances of heavy elements often showed only weak signals from these carbon structures. There were two main possibilities. They might be difficult to form when carbon and dust are scarce, or they might still be created but quickly destroyed by intense radiation. Observations of sextans A opened the door to a more subtle explanation. The carbon structures were not completely absent. They were concentrated within a few small, relatively dense pockets of gas, where surrounding material shielded them from some of the damaging radiation. If the entire galaxy were observed at low resolution, the faint signal from these pockets would blend into the background and nearly disappear. Webb was sensitive and precise enough to separate them from the surrounding space. The locations of these clusters suggest that the problem is not simply that small dust particles are being destroyed. Their formation and growth also seem to operate efficiently only where the conditions are suitable. Denser gas allows atoms and molecules to encounter one another more often. The surrounding material reduces the amount of radiation that can penetrate inward. Fragile carbon structures are given more time to develop before being carried into a harsher environment. This picture changes the way we think about a galaxy that appears almost devoid of dust. Dust does not necessarily form evenly throughout space. It may begin in isolated places, around certain aging stars with unusual conditions, within parts of supernova ejecta, and inside sheltered pockets of cold gas. Most of the galaxy may remain poor in solid matter, while a few small regions quietly become sites where dust is formed or allowed to grow. Once even a small amount of dust is present, it can provide additional shielding for the gas behind it. A better protected environment allows some molecules to survive longer and creates conditions in which new layers of material can collect on grains that already exist. This process does not have to be rapid or uniform, but it makes it possible for a region containing very little dust to gradually become more favorable for further grain growth. Here, we reach one of the most important points in the journey. Stars may create the first seeds, but the space between stars is not merely a passive destination. Within clouds that are cold and dense enough, grains continue collecting matter. Some of a galaxy's dust is born around stars, while another portion is completed within dark regions that light can barely penetrate. Not every aging star in sextans A produces large amounts of dust, and the carbon structures were found only in limited clusters. The scarcity of heavy elements still has a powerful effect. Webb does not show that dust forms easily everywhere. It shows that nature has more than one way to work around a shortage. Where a familiar pathway is restricted, another material may become important. Where most of space is too harsh, a small pocket of gas may provide the protection required. Sextans A is therefore not a replica of the first galaxies, nor does it contain the oldest dust grains preserved intact. Its value lies in allowing us to examine a nearby environment poor in heavy elements. Scientists can separate the light of individual stars, identify the material surrounding them, and trace small concentrations of dust between the stars. These details help explain the faint, blended signals arriving from galaxies much farther away. It is also important to remember that Webb images are not color photographs in the way human eyes would see them. Infrared light is translated into visible colors so that different structures can be displayed more clearly. The beauty of the images is real in the sense that they are built from genuine data, but the colors are a method of representation. The scientific evidence lies in the amount of light measured at each wavelength and in the subtle changes across the spectrum, not in whether a cloud appears blue, yellow, or red on a screen. Through these measurements, dust gradually tells a history that it cannot preserve as one complete narrative. Dimmed light reveals material lying along the line of sight. Infrared energy shows where the dust is receiving its heat. The shape of the spectrum suggests what kinds of grains were formed, while their location reveals which environments allowed them to survive and grow. Every conclusion is assembled from many pieces. A single feature may have more than one explanation, but when location, brightness, stellar temperature, and spectral shape all point in the same direction, the picture becomes more secure. The uncertainties are not weaknesses that need to be hidden. They mark the places where new data may change the way we understand matter in young galaxies. The discovery in sextans A leaves us with an idea deeper than the names of any particular materials. A chemically primitive environment is not necessarily a simple one. When the ingredients common today were still scarce, matter did not merely produce less. It followed different pathways, created different mixtures, and gathered in different places. Scarcity did not erase the possibility of dust formation. It made that possibility more selective. The first dust grains in the universe have still not been found as individual objects. We do not know whether the first grain was rich in carbon, silicon, or some kind of oxide, nor do we know how long it survived before being destroyed. Webb does not carry us all the way back to the moment when the first solid particle appeared. But observations like those of Sextans A reveal how inventive matter can be when only a limited supply of ingredients is available. From here, the story begins to change direction. Dust is no longer only evidence of what stars accomplished in the past. As tiny grains enter clouds of gas, they absorb light, shield molecules, and provide surfaces on which chemistry can continue. They take part in cooling the material, move into regions that are beginning to collapse, and eventually appear within disks rotating around young stars. A dust grain may begin as matter condensed around a dying star, grow further in the darkness between stars, and then be carried into a region where a new star is forming. This journey moves material from the remains of one generation into the raw ingredients of the next. As the number of grains increases, they begin changing not only the way the universe is observed, but also the way the universe builds new structures. The universe was once completely transparent in the absence of dust. When dust appeared, some light became obscured. Dark regions began to form, and space grew more difficult to see through. Yet those darker places created the conditions for cold gas, stable molecules, and eventually solid worlds to emerge. Dust took away some of the universe's original transparency, while giving it possibilities that a simple ocean of hydrogen and helium had never possessed. After leaving the stars that created them, dust grains may drift through a galaxy for longer than the entire histories of many hypothetical civilizations. They do not travel in straight lines, nor do they retain the same form throughout the journey. At times, a grain passes through hot gas, where fast-moving ions continuously erode its surface. At other times, it is swept up by a shock wave, accelerated, and then slowed again as it collides with the surrounding medium. In quieter regions, new atoms attach to its outer layers, changing the composition it carried from its birthplace. Some grains are destroyed completely, returning to the gas and waiting for another opportunity to condense. Those that survive long enough may eventually enter cold clouds, where their role begins to change in profound ways. In the space between stars, gas is not distributed evenly. Most of the volume is extremely thin, but in certain regions, gravity and the motion of the galaxy gather matter into clouds tens or hundreds of light years across. Seen from the outside, a dust-rich cloud often appears as a dark band obscuring the stars behind it. That darkness is not an empty space. It is evidence that light is being absorbed and scattered by countless tiny grains mixed throughout the gas. The ability of dust to block light creates a change. that a universe containing only hydrogen and helium could not produce in quite the same way. Ultraviolet radiation from young stars carries enough energy to break apart many molecules. In gas fully exposed to intense light, newly formed bonds may quickly be destroyed. When dust in the outer layers absorbs some of that radiation, the deeper regions of the cloud become chemically quieter. Temperatures fall, molecules survive longer, and slow reactions are given more time to unfold. Dust makes a region of space darker, but that darkness does not mean that activity has stopped. Inside the cloud, matter continues moving under the influence of heat, magnetic fields, turbulence, and gravity. Denser regions draw in more gas. Streams of material collide, creating long filaments and compact knots. Energy is constantly exchanged among gas, dust, and radiation. Shielding simply changes the rhythm of this activity, allowing certain regions to become colder and denser before external light can destroy the fragile structures taking shape within them. Temperature partly determines how well a cloud of gas can resist gravity. Hot gas contains rapidly moving particles that create outward pressure. As the gas loses energy, those motions slow and the pressure decreases. Gravity can then pull the matter inward more effectively. Atoms, ions, and molecules help cool the gas by absorbing energy in collisions and releasing it as light. Dust adds another pathway. Gas particles strike grain surfaces, transfer some of their energy to the solid material, and the grains then radiate that energy away as infrared light. Not every cloud depends on dust to the same degree. In more diffuse gas, atoms and molecules may play the main role in cooling. As density increases and the interior becomes better shielded, the exchange of energy between gas and dust becomes more important. Chemical composition, grain size, and radiation intensity determine which mechanism dominates. Dust does not replace every other process, but it broadens the range of conditions the gas can reach. The first stars formed when almost no dust existed, so solid matter is not an absolute requirement for star formation. Primordial gas could still cool through small amounts of molecular hydrogen and other processes. The difference lies in how much the cloud can fragment. When gas struggles to lose heat, collapsing regions tend to remain larger. When heavy elements and dust create additional cooling pathways, the cloud can divide into smaller regions before each one continues contracting. This division is not like a solid object cracking into separate pieces. A gas cloud has no fixed boundaries and is always being disturbed. Tiny differences in density grow as denser regions attract more matter. Turbulence may compress gas in one place while allowing it to expand in another. Magnetic fields redirect the flow of material, while light from nearby stars may heat or blow away the outer gas. Amid all these influences, the ability to lose heat helps determine which regions remain dense long enough for gravity to continue its work. Even a very small amount of dust can become important once a cloud reaches high density. Dust grains provide additional surface area, absorb radiation, and help the gas release energy. In models of the young universe, the appearance of dust is considered one factor that may have allowed low-mass stars to form from gas, poor, and heavy elements. The exact threshold still depends on the type of dust, how many grains survived supernovae, and how much they grew in the interstellar medium. No single value applies to every cloud, but the direction of the change is fairly clear. Once solid matter appears, gas gains more ways to enter colder and denser states. On large scales, gravity remains the force that turns clouds into stars. Dust does not guide matter according to a plan, nor does it decide how large a star will become. Its influence lies in changing the initial conditions, much as a small ingredient can alter the temperature and pace of an entire process. The size of each individual grain is almost negligible, but the combined surface area of countless grains spread throughout a cloud can be enormous. Those surfaces provide another place for the chemistry of space to unfold. In thin gas, two atoms may take a very long time to encounter one another. Even when they collide, they may not remain bonded because the excess energy must be transferred somewhere. A dust grain offers a surface where an atom can temporarily attach, lose some energy, and move a short distance before meeting another component. Molecular hydrogen is one of the clearest examples. Each molecule consists of two hydrogen atoms bonded together, but forming a stable bond through a single collision in the gas phase is often inefficient in many parts of the interstellar medium. When two atoms attach one after another to the same dust grain, the distance between them becomes much smaller. They can meet on the surface, form a bond, and transfer the excess energy into the grain. The new molecule can then leave the surface and return to the gas. Molecular hydrogen existed before dust became widespread, because the primordial universe had other pathways for creating it. After dust appeared, grain surfaces became efficient production sites in many clouds of the modern universe. This molecule not only makes up most of the matter in star-forming regions, but also contributes to the cooling and shielding of the cloud. A new cycle gradually emerged. Stars created heavy elements. Those elements condensed into dust. Dust supported the formation of molecules, and molecule-rich clouds became the birthplaces of the next generation of stars. As a dust grain moves deeper into a colder region, its surface begins collecting other materials. A water molecule striking the grain may remain attached instead of bouncing away. Carbon monoxide, carbon dioxide, methane, ammonia, and many other volatile substances also freeze onto the surface when the temperature becomes low enough. Over time, a thin mantle of ice forms around the solid core. Interstellar ice is not composed only of water like the ice covering a winter lake. It is a mixture of many molecules frozen onto the grain. Their proportions vary with location, temperature, and gas composition. A grain with a silicate core formed around an aging star may later acquire a carbon-rich coating in the interstellar medium, then become surrounded by ice after entering a cold cloud. That tiny structure preserves several stages of its journey, even though none of those stages lasts forever. The icy surface continues receiving energy from weak ultraviolet light that still penetrates the cloud and from high-energy particles moving through space. This energy can break certain bonds and allow the fragments to rearrange into new molecules. Many experiments that reproduce interstellar conditions have shown that simple mixtures of ice can form more complex compounds when exposed to radiation and later warmed. This should not be taken to mean that life naturally appears on every dust grain. The distance between an organic molecule and a living system remains immense. Surface chemistry simply increases the diversity of matter, creating some molecules that may be much harder to form in the gas phase. When the environment around a grain becomes warmer, many components of the icy mantle return to the gas, making the regions around young stars chemically richer. While these reactions unfold across tiny surfaces, the cloud continues changing on a much larger scale. Some knots of matter become dense enough for gravity to overcome both turbulent motion and internal pressure. Gas begins falling toward the center. The central region grows denser and warmer, gradually becoming a protostar. Material from farther out continues to stream inward, carrying with it dust grains that have already passed through many generations. The motion of the cloud is rarely directed perfectly toward the center. Every region of gas carries at least a small amount of rotation, even if it is almost impossible to notice at first. As the cloud contracts, that rotation speeds up because angular momentum is conserved. The material cannot fall directly into the protostar all at once, so it spreads into a rotating disk around it. Within this disk, gas and dust enter the stage that may eventually lead to the construction of planets. Temperature is not uniform throughout the disk. Close to the protostar, radiation and friction heat the material so intensely that many compounds cannot remain solid. Farther out, silicates and metals can survive. In still colder regions, water and other volatile substances freeze onto grains. These temperature boundaries move as the young star changes in brightness and the disk gradually loses material, which means that the same location may pass through several different conditions over time. Dust grains in the disk are influenced by more than the gravity of the star. Gas orbits at a slightly different speed from solid particles because it is also supported by pressure. Small grains remain tightly coupled to the gas, while larger grains begin moving more independently. This difference causes them to drift through the disk, gather in certain regions, and collide more often than they did when they were scattered throughout the wider cloud. The earliest collisions usually occur at low speeds. Two very small grains may stick together through weak surface forces, especially if their shapes are irregular or coated with ice. The new cluster is not a solid stone, but a porous structure made of many smaller particles loosely holding onto one another. It continues colliding with other clusters, growing larger and gradually becoming more compact. Growth does not follow a smooth path. As the particles become larger, their relative speeds also increase. Some collisions cause two clusters to merge, others merely compress them, and some are energetic enough to shatter the objects into smaller fragments. Those fragments return to the cycle, continue drifting with the gas, and may later attach to other bodies. A protoplanetary disk is an environment where matter is constantly being assembled and broken apart. The gas creates another obstacle as well. Some grains grow to sizes at which drag causes them to lose orbital energy very quickly and drift inward. Without a mechanism to concentrate them or help them grow fast enough, they may fall into the star before becoming larger bodies. This was once one of the central difficulties in explaining how tiny dust grains could become objects kilometers across. Current observations and models show that disks are not perfectly smooth environments. Regions of higher pressure can trap particles and slow their inward drift. Gas vortices, boundaries between temperature zones, and structures shaped by magnetic fields may all gather dust into narrow regions. Once the concentration of grains becomes high enough, the particles begin influencing the gas in return and become even more tightly concentrated. Gravity between the clusters can then begin to matter, helping the material collapse into bodies large enough to no longer be controlled entirely by the gas. Objects kilometers in size are often called planetesimals, even though they are still far from becoming complete planets. Once they form, they collide under the influence of gravity and build larger planetary embryos. The process continues through many generations of impacts, and not every encounter leads to growth. Some bodies are shattered, some are scattered onto new orbits, and some are ejected from the system altogether. As a planetary embryo gains mass, its gravitational field draws in material from a wider region. Collisions release energy and heat the interior. Radioactive isotopes still present in the material contribute additional heat. If temperatures rise high enough, metals and silicates melt or soften, allowing the different components to separate according to density. Iron and nickel tend to sink toward the center, forming a metallic core. Lighter silicates create the mantle and crust. New minerals appear under pressures and temperatures very different from those in which the original dust condensed. A rocky planet is not simply a compressed pile of dust that remains unchanged. It is the result of countless episodes of heating, collision, melting, separation, and recrystallization. Although the final structure has been transformed completely, its ingredients still came from the tiny particles within the disk. Silicon and oxygen became the foundation of many minerals. Magnesium and iron entered silicate structures, while some of the iron descended into the core. Aluminum, calcium, and other elements became part of minerals formed under different conditions. Every component carried a history that began before the planet existed, inside stars that had lived and died long before. In the colder parts of the disk, grains carried more ice. Bodies forming there retained larger amounts of water, carbon dioxide, ammonia, and other volatile substances than those forming closer to the star. When icy objects were disturbed from their original orbits and moved inward, they could collide with growing rocky planets. Some of the water and volatile material on a planet may have arrived in this way, in addition to what was already present in the region where the planet first began forming. The origin of water is not the same for every planet. The distance at which it formed, the temperature structure of the disk, the migration of giant planets, and the history of collisions all influence the outcome. Ice-coated dust remains an important part of the story because it allows volatile molecules to be preserved within solid bodies long enough to travel across different regions of space. Dust disks around young stars do not exist only in theoretical models. Telescopes have observed many systems at different stages of formation. At infrared and radio wavelengths, the disks appear with bright rings, gaps, curved arcs, and spiral structures. Some of these features may be created by newly forming planets as they pull material away from nearby orbits. Others may arise from changes in pressure, the freezing of molecules, or the internal motion of the gas. Not every gap in a disk is certain evidence of a planet. Interpretation requires combining the size of the structure, the motion of the gas, the distribution of particles, and the age of the system. Even so, the observations clearly show that dust does not remain motionless in a smooth, uniform layer. It gathers, migrates, changes size, and becomes part of structures that may eventually lead to planets. Larger grains absorb and emit light differently from smaller ones, so the spectrum of a disk can reveal clues about grain growth. Polarized light provides information about particle shape, alignment, and approximate size in the outer layers. Longer wavelength observations allow astronomers to see colder material closer to the disk's midplane. No telescope can follow each grain individually, but the combined signal from countless particles reveals matter moving from fine dust toward larger and more complex structures. If we trace the history of a grain of sand backward, the geological layers of Earth gradually disappear. Before them came the hot material of the young planet. Before the planet came, smaller bodies colliding within the disk around the Sunday. And before those bodies came countless dust grains drifting through the cloud that gave birth to the solar system. Farther back still were aging stars and supernovae that returned carbon, oxygen, silicon, and iron to the Milky Way. At the beginning of that chain was a universe with no surfaces for water to flow across, no minerals to reflect light, and no solid grains for molecules to settle upon. Ordinary matter consisted almost entirely of light elements. Gravity could create stars, but it could not yet build a rocky planet because the necessary ingredients had not been born. The appearance of dust did not immediately create worlds like Earth. It only opened the first step in a different process. Tiny grains carried matter from stars into clouds, from clouds into disks, and from disks into growing bodies. Through countless failures, episodes of destruction, and cycles of rebuilding, some of that material eventually became part of planets. Dust is therefore a bridge between what has ended and what has not yet appeared. It carries the products of dead stellar cores into regions where new stars are forming. No grain knows where it is going, and no outcome is predetermined. Most journeys end in hot gas, inside a star, or in collisions that break matter apart. Only a small number of paths lead towards solid worlds. The universe became less transparent when dust appeared, because light began to be trapped within dark clouds. Along with that loss of transparency came colder regions, chemically active surfaces, and reservoirs of material capable of gathering into planets. Darkness did more than conceal matter. In many places, it created the quiet conditions matter needed to rearrange itself. From an ocean of gas composed almost entirely of hydrogen and helium, the universe gradually produced heavy elements, solid grains, molecule-rich clouds, and disks filled with the raw materials of planets. Carbon gained countless new ways to form bonds. Silicon and oxygen could combine into minerals. Iron entered dust grains, planetesimals, and eventually the cores of larger worlds. A single dust grain cannot build a planet by itself. Even trillions of grains still require gravity, gas, time, and countless collisions to move any further. Yet without the first solid surfaces, matter would have lacked a starting point for the long process of accumulation that created rocky planets. The transformation began on scales smaller than a human hair, but its results could extend across worlds thousands of kilometers wide. Grains formed around aging stars do not need to survive intact until the end of the journey. They may be destroyed while their atoms continue into other grains. The importance of dust does not lie in the permanence of individual objects, but in matter's ability to return again and again to a solid state. With every cycle, the universe preserves more pathways for building complex structures. In this way, grains that began as fragile products within cooling gas became part of star-forming clouds, layers of molecular ice, and protoplanetary disks. They passed through many transformations before appearing in the rock, metal, or water of a new world. No single moment completed the transition from primordial gas to planet, but dust stood between nearly every important stage of that journey. The early universe had light before it had dust. After dust appeared, the darkness between stars took on a new meaning. Within obscured regions, gas could cool, molecules could survive, and matter could gather around young stars. Some light was held back, but that very concealment opened the path towards structures that light would one day illuminate. From tiny surfaces too small to be seen individually, nature gradually built larger ones. The rock of asteroids, the crusts of planets, mountain ranges, ocean floors, and countless grains of sand resting along the edges of seas. Every one of those surfaces belongs to a history that began when the universe first possessed enough elements to create a solid grain, and enough time for that grain to become part of a world that had not yet been born. The shoreline still rests beneath the night sky, while the tide continues moving to a rhythm that had repeated for ages before anyone stood here to listen. Across the damp sand, tiny grains reflect a portion of the faint light from the stars. They have passed through water, wind, and the gradual erosion of stone, yet their deepest history began before Earth had oceans, before the sun began to shine, and even before the Milky Way took on the familiar shape it has today. The silicon within a grain of sand was once created in the heated layers of a star. The oxygen bonded to it also came from generations of stars that lived and died before the solar system appeared. The iron contained in darker minerals has passed through explosions, clouds of gas, and cycles of renewal lasting billions of years. None of those atoms knew they would one day become part of a shoreline, and the universe did not guide them toward a predetermined result. Matter simply continued changing under the influence of gravity, heat, light, and time, until some of its countless paths happened to lead toward worlds with solid surfaces. In the earliest ages, no such surfaces existed. The universe contained mainly hydrogen and helium, enough to form enormous clouds of gas and the first stars, but not enough to build stone. The periodic table was still almost empty. Carbon, oxygen, silicon, and iron began to appear only when the first stars transformed light nuclei into heavier structures within their cores. The birth of new elements did not immediately create dust. Matter first had to escape from stars, spread into space, and cool. Atoms had to meet, form tiny clusters, and preserve their bonds within an environment always capable of breaking them apart. The first solid grain probably did not appear in a brilliant moment. It may have emerged quietly inside a fading cloud of gas, many times smaller than anything the human eye could recognize. That first grain may have been destroyed long ago. Perhaps it survived for only a few years, a few thousand years, or long enough to enter another cloud. Its individual fate can no longer be traced. What mattered was the possibility it represented. From the moment matter could remain solid in the space between celestial bodies, the universe gained another way to build structure. Stars continued creating elements, explosions continued distributing them, and new grains of dust formed again and again. Some were destroyed by shock waves, others grew inside cold clouds. On their surfaces, atoms and molecules encountered one another under conditions that the gas phase could not easily provide. Dust absorbed light, darkened regions of gas, and created sheltered spaces where matter could cool and fragile molecules could survive for longer periods. From then on, the darkness between stars was no longer merely the emptiness separating sources of light. Within many dark clouds, gas was contracting, dust grains were carrying mantles of molecular ice, and new stars were slowly taking shape. Around young stars, dust gathered into disks, colliding and sticking together through countless unsuccessful attempts. Most of the material was shattered or fell into the star, but some continued growing into bodies with gravity of their own, and eventually into planets with metallic cores and rocky crusts. Not every planet has oceans, and not every world with water develops life. Dust guarantees none of these outcomes. It simply expands what matter is capable of doing. A universe that once contained only gas could now create minerals, ice, surfaces, and increasingly complex chemical environments. From those possibilities, some worlds followed paths stable enough to endure for billions of years. Earth is one of those worlds. Elements once created inside stars entered the young planet, where they were melted, separated into layers, and reshaped through geological activity. Iron sank deep into the interior, silicon and oxygen formed most of the planet's rock, and water, wind, and changing temperatures gradually wore great masses of stone into smaller grains. A grain of sand on a beach is not an intact piece of stardust, but it is built from matter that no planet could have created on its own if earlier stars had never existed. When we lift a grain of sand, we are touching a very late part of that story. There is no clear boundary between the history of stars and the history of planets, because the same atoms have passed through both. They have existed within hot plasma, cold gas, dust grains, the disk around the young sun, molten rock, and finally a mineral carried onto the shore by ocean waves. The universe did not begin with everything already complete. It began with a very small collection of simple ingredients, then gradually created new possibilities through each generation of stars. Light came before dust. Stars came before planets. Heavy atoms came before surfaces capable of holding water. Every familiar structure around us is the result of a long history in which matter was continuously created, broken apart, and rearranged. Beyond us, that process has not ended. Aging stars are still shedding their outer layers. Supernovae are still scattering elements throughout their galaxies. Inside cold clouds, dust grains are still growing, while around young stars, disks of matter are quietly building worlds that do not yet have names. Many of those worlds may never possess seas, mountains, or living beings capable of looking into the sky, but they still belong to the same cycle that transformed primordial gas into solid matter. Along the shoreline, another wave moves in, shifting the positions of millions of grains of sand within a few seconds. Each grain travels only a tiny distance compared with the journey already taken by the atoms inside it. Against the motion of the galaxy, the lifetimes of stars, and the history of matter, the beach is only a temporary resting place. And yet, from this small resting place, the universe can look back upon itself. Elements created inside stars became a world with a surface, and upon that surface appeared beings capable of tracing light and asking about the age before dust. Matter did not only create mountains, oceans, and living bodies. Through us, part of that matter can also recognize just how long its journey has been. Long before there were oceans, before mountain ranges rose or sandy shores rested beneath the night sky, the universe first had to learn how to create a grain of dust. From that first tiny solid particle, new possibilities slowly opened, until the darkness between the stars could hold clouds, planets, and a quiet place where the story of its own origin could be heard.